All right, so today it's going to be a pretty short video on the strength of an acid and how we can tell. So a couple things you need to be aware of is that pretty much a ton of things have hydrogen in them. That does not necessarily mean that they're an acid. So by definition, Bronsted-Lowry acid has a hydrogen. Typically, just having a hydrogen does not make you an acid. So how do we know that we do have an acid? Well, there's two things. One, the strength of the bond and the polarity of the bond determine whether or not you're acid, and then how strong of an acid you actually are. So let's take a look here. These four different compounds, HF, HCl, HBr, and HI, they are all acids. We know this to be true. Now, you would think that because HF is the most polar, which means that the electrons in that bond, so if I have an HF, if I were to take a look at the electrons in there, they would shift dramatically towards the fluorine, kind of leaving this little hydrogen out to dry, able to be plucked off by anything else, correct? Yeah, you'd think that. But what we discover is that of these four, even though HF is the most polar, it's actually the weakest acid. And that's because not only does the polarity of the bond determine how good of an acid you are, but how strong the bond is. And if you take a look here at bond strength down below here, it's kind of hard to see, but if you take a look, you see how HF has a bond strength of 565, which is much, much stronger than these other bonds, which means that this bond right here, this HF bond, this bond right here, it's really strong. It doesn't want to break apart. And part of the reason is that fluorine is really, really small. And again, we get to that thing of whenever you have things that are really, really small, they tend to hold on really, really tightly. So this hydrogen is actually held pretty tightly by the fluorine. And even though it's very polar, it's actually a pretty weak acid in water. Whereas you have things like HCl, HBr, and HI in particular, which is not very polar at all comparatively to this, it actually is a really, really good acid. And in fact, if you take a look at these three right here, aren't they part of our CBS pin? Now, the other thing you can take a look at is how do we know whether or not something's really polar? So I want to take a look at this chart, and these, by the way, are in your textbook. But if you take a look at what our central atom is, so it's maybe hard to see, but in all these cases, we have an H attached to an O, and then we have some body right here, which we call X. And they put the X part as either Cl, Br, I, or enjoyably CH3. And what you discover is that the more electronegative that this X is, the more the overall electron density shifts away from the hydrogen and the better an acid it becomes. So if you take a look at Cl, do you see how the Ka for the acid is of HOCl, by the way, it's not HCl, is 4 times 10 to the negative 8. But then if you take a look at HOBr and then HOI, it goes 10 to the negative 9, 10 to the negative 11. That's because in both these cases, take a look at the 2.8 and the 2.5, the electronegativity of the atom that's attached to the OH is lower. If you take a look at CH3, which is just a carbon, and there is no electronegativity pull essentially on this, you end up with this really, really weak acid. Yeah? Now, let's take a moment here. You guys see my drawings in the background here. What if we have a bunch of oxygens or oxoacids? So we call these oxy acids, and that's because they have oxygens in them, yeah? And what we note is this: the more oxygens that we have on the outside pulling away from the proton that wants to leave. So in all these cases, this hydrogen is the proton or hydrogen that wants to leave. And if you take a look, each of these three O's over here, they pull electrons along with the Cl towards themselves, pulling it away from this bond right here and weakening this bond. Here you have just two pulling away, here you have just one, and here you have none. And if you take a look at the Ka values, if you have HClO4, which is 3 oxygens attached to a Cl, then attached to O, then attached to H, which is essentially what this bottom diagram is right here, you end up with a Ka that is incredibly large. If you take a look at HClO2, which is this guy right here, you have I'm sorry, HClO3, not HClO4, but 2 oxygens on the outside here. You have a Ka of about 1, which is not bad, right? But it's not a strong acid. And then if you take away oxygens, you go down to here where HClO by itself is a pretty weak acid. Same thing works for H2SO4. If you take a look at H2SO4, you see how there's a sulfur and it has 3 oxygens pulling electrons towards it. And then you see how you have an O and an H, and then you have another O and an H. So this O right here, that's the proton that gets pulled off first. This H, not O. This H right here, that's the second one that gets pulled off. The first hydrogen to be pulled off, it takes almost nothing to pull it off because all of the electron density has moved away from it. So it has an incredibly large Ka, which is why H2SO4 is a strong acid. If you look at H2SO3, however, do you see how it only has 1, 2, 3 oxygens onto it, and it has the same 2 hydrogens that are pulling away from it. Therefore, it's not going to pull away quite as much, and its overall Ka is going to be pretty low. So the general rule is this, and we'll write it down here: more oxygens, stronger acid. That is a general rule, and typically what you end up happening is with an oxo acid, you have a hydrogen attached to an oxygen, and then it's attached to something. The more electronegative that something is, or the more O's you have, the greater the electron pull is going to be in this direction, and the weaker this bond is going to be. So that's a quick snapshot of what makes acids stronger or weaker. Hope this helps.